Hello, everyone. Welcome to the Chapter 14 narrated PowerPoint. This is the first of two PowerPoints that's going to cover mountain building, what's also called orogenesis. And in this introductory slide, all I'm really attempting to show you is where Earth's continental mountain belts occur. And you can see by the different colors the relative ages of these different mountain belts. So, for example, if we first focus along the west coast of North America, Central and South America, we have relatively young mountain belts in that area. But we could also focus on the east coast of North America and also in sort of Central Asia and Eastern Australia, and we can see older mountain belts in these areas. So the take-home message of this slide is that mountain belts, also known as orogens, occur all over the world. And what we're going to explore in this chapter is how continental mountain belts are put together, how they form. Luckily, we're on the right side of the plate tectonic revolution, but obviously before plate tectonic theory was developed in the early to mid 1960s, geoscientists really didn't understand very well how continental mountain ranges were put together. And they had a lot of ideas, many of which have been disproven. And one particularly interesting idea is the so-called shrinking Earth hypothesis. And the idea is that as the Earth cools, it shrinks and in effect shrivels up, sort of like an apple left in the sun. And perhaps the shrivels represent mobile mountain belts. It's a very interesting and even a very intuitive idea, except for the fact that it's completely wrong. Then again, these ideas, such as the shrinking Earth hypothesis, were developed before plate tectonic theory arrived on the scene. And so it was really only in light of later research, thanks to plate tectonic theory, that geoscientists were able to disprove some of these earlier ideas, like the shrinking Earth hypothesis. And you can see that quote down on the bottom of the slide by Robert Hill. And Hill said, quote, "The rocks are being folded, fractured, and otherwise broken or deformed by the great shrinking and settling of the Earth's crust." So again, interesting idea, except for the fact that it's completely wrong. Luckily for us, we're on the right side of the plate tectonics revolution. And so already in the course at this point, I think you have a pretty good understanding of how continental mountain belts are made. Namely, they occur at convergent plate boundaries, subduction zones and collision zones. And just very quickly, this is more of a review than anything. Of course, at a subduction zone, as shown in the left-hand diagram, this is where an oceanic plate, that's just a plate topped by oceanic crust, sinks into Earth's interior beneath either another oceanic plate or, in the case of this chapter, a continental plate. And that's what we call a subduction zone. And then over on the right-hand side, we have an image of a collision zone. Think of plate collision as continent-continent plate convergence, where two continental plates sort of smush together horizontally to create mountains. And in this case, because both continental plates are relatively buoyant, they don't subduct. That is, neither plate subducts appreciably beneath the other. Instead, both plates just sort of crunch together to create a lot of lithospheric shortening and a lot of lithospheric thickening to create continental mountain ranges. Okay, so that's the take-home message here. Continental mountain building is a result of both collision and subduction. Something we haven't touched on yet in the course, and it's very important when we start considering continental mountain building, is how the lithosphere moves vertically rather than horizontally. So up until now in the course, we've talked about how the lithosphere slides around horizontally atop a more mobile asthenosphere. But it turns out that at origins, that is continental mountain belts, the lithosphere is being lifted skyward vertically. It's not simply moving horizontally. And so we have to talk about a really important process that allows this vertical movement of the lithosphere to happen. And that process is known as isostasy. And you can see there in the slide that isostasy is simply the buoyant equilibrium, ultimately a balance of forces between the lithosphere and the underlying asthenosphere. So I'm going to highlight this definition. It's a really important one. Don't worry, we're going to refer to it a lot in this chapter. But you'll be able to make sense of isostasy if you just keep in mind that ultimately it's a competition or a balance of forces. And let me first give you an analogy, and then we'll attempt to say a little bit more about the two forces involved in isostasy that kind of counterbalance each other. So imagine that we have lithosphere right here. And let's imagine that we weigh down the top of the lithosphere by a really thick, really heavy ice sheet. Because we can think of the lithosphere as essentially floating within and on top of the underlying asthenosphere, when we add additional mass to the top of the lithosphere, it's going to sink a little bit into the asthenosphere. And it's kind of like an iceberg in water, right? If you imagine an iceberg floating in water, what would happen to that iceberg if we piled up a lot of mass on the top of the iceberg? Maybe we added a bunch of weights to the top of the iceberg. Maybe we just added more ice to the top of the iceberg. Well, if the iceberg's floating in water, probably you can appreciate that by adding more mass, more stuff to the top of the iceberg will sink downward into the water a little bit. And likewise, we can have isostatic rise, that is uplift, when the opposite happens. So in this case, imagine we're weighing down the lithosphere due to a heavy ice sheet sitting on top of it. And then let's imagine that we have rapid climate change and the ice melts. So no more ice. And at this point, then the lithosphere can rise upward. And here I'll make an analogy instead of with an iceberg, with a cargo ship floating in water. Imagine that we've loaded down the cargo ship with a lot of heavy freight containers. The cargo ship, when we add the containers, is going to sort of sink lower into the water. That's isostatic loading, also known as isostatic subsidence. But now when the cargo ship pulls into port and the ship is empty, that is, the heavy cargo containers are removed from the ship, maybe you can appreciate that the ship will actually rise upward. It'll float higher on the surface of the water when it's empty than when it's weighed down with a bunch of cargo containers. And so back to the iceberg analogy, when the ice melts, that additional load, that additional mass is removed, and the lithosphere will actually pop up a little bit like a cork as a result of the removal of the heavy ice sheet. Okay, so that's the essence of isostasy, and it's the main process by which the lithosphere can move vertically upward and also downward. And I mentioned earlier, you can kind of see there in that definition that ultimately isostasy is the result of a balance of forces. Well, what two forces are we talking about here? Well, we're talking about gravity and buoyancy. These are the two forces that oppose each other in isostasy. I think we're all pretty familiar with gravity, and it's simply the idea that the gravitational force is in effect pulling the lithosphere downward towards Earth's center. I think that's pretty obvious to everyone. And then what we're going to discuss in the next couple of slides is maybe something that's not intuitive to a lot of us, and it's known as the buoyant force. And the buoyant force opposes gravity in that it pushes upward on the bottom of the lithosphere. And it's ultimately a result of the fact that pressure increases with depth within the lithosphere and also the asthenosphere. So we'll get to that in a minute here. But for now, I just really want you to appreciate that isostasy is ultimately a balance of forces. Which two forces? The gravitational force wanting to pull the lithosphere downward, and the buoyant force wanting to push the lithosphere upward. Okay, well, let's look at the gravitational and buoyant forces in just a bit more detail. Please don't be too intimidated by this slide. I am listing a couple of mathematical equations, and there's some physics concepts that we're going to cover here. But I want to assure everyone we're not going to actually solve these equations. You're not going to be doing isostatic math on the next quiz. We're really just after the concepts here. And sometimes if we add a little math to the concepts, it makes the concepts a little bit more clear. And that's all I'm trying to do here. So don't freak out when I start talking about these equations. Okay, well, over on the left is the main equation for the gravitational force. The gravitational force can be abbreviated, if you will, by the letter F and then a little small subscript G just to the right of the F. So we would say F sub G. That's the gravitational force. And in this case, it's the gravitational force on a theoretical ball. So we have a ball, and what's the gravitational force acting on that ball near Earth's surface? Well, it's just the mass of the ball. That's m subscript ball right there, times acceleration due to gravity. That's how we calculate the gravitational force on the ball. Again, that's just gravity acting on the ball itself. And as I said, the gravitational force is always oriented downward. It's wanting to pull the ball, or in our case, the lithosphere, downward towards Earth's interior. Okay, that's the gravitational force, and I think most of us are familiar with that. The buoyant force, on the other hand, is an upward directed force. You can see it right here, capital F subscript B. That stands for the buoyant force, and the buoyant force is always directed upward. If you want an equation in order to calculate the buoyant force, I've listed it for you right there. The buoyant force is just equal to the density of the fluid. In this case, not the density of the ball, but the density of the fluid the ball is submerged in. And we're going to multiply that by the acceleration due to gravity and also by the volume of fluid displaced by the ball. Now in this case, because the ball is entirely submerged in the fluid, the ball is completely underwater here in that right-hand diagram, the volume of fluid displaced by the ball would just be equal to the volume of the ball itself. And in this case, we're assuming that the ball is more like a beach ball. In other words, it's not absorbing water like a sponge. There's no water inside the ball. Okay, so again, you're not going to need to even remember the equation for the buoyant force or the gravitational force. I just wanted to show you what those equations look like. And okay, now I want to talk a little bit more about how the buoyant force arises. So over on that right-hand diagram, of course, we have a ball. Let's imagine that it's a round beach ball, and it's submerged in water. It's completely underwater or in some kind of fluid. We'll say it's water. And probably you can appreciate that if you go deeper and deeper below the surface of the water, water pressure increases as a function of depth. The deeper you go beneath the water surface, the greater the water pressure is in relation to depth. And you probably have felt this yourself if you've ever dove down to the bottom of a swimming pool. You know that more than a few feet below the water surface, your ears start to hurt. And that's just because the higher fluid pressure at a greater depth, the water pressure, is pressing in on your eardrums and it hurts. And then when you come up to the surface, there's less water pressure pressing in on your eardrums, and so the pain goes away. So back to our theoretical ball submerged in water, can you appreciate that the fluid pressure on top of the ball, right here, is actually less than the fluid pressure pressing upward on the bottom of the ball? How come? Well, the bottom of the ball is just in deeper water than the top of the ball. And so the bottom line here is there's more pressure pushing the ball upward in this case on the bottom of the ball than there is pressure pushing downward on the top of the ball. And when you add those two forces together, then you get a net upward force. That's what the yellow, or rather the red arrow, represents. That's the buoyant force. And we represent the buoyant force as capital F subscript B. So there it is right there. And there it is right there. And again, it's always directed upward towards the sky, as opposed to the gravitational force, which is always directed downward toward the Earth's interior. Okay, so that's what the buoyant force is. It's a net upward force on a submerged object, or even a floating object, frankly, that opposes gravity. Okay, here's a simple rule that I want you to remember, much more so than the equations in the previous slide. So for a ball submerged in water or any kind of fluid, there are two forces at play: the buoyant force, which is directed upward, and the gravitational force, which is directed downward. And now we can ask ourselves, well, how is the ball going to move when it's submerged in that fluid? Is it going to sink down to the bottom of the fluid, or is it going to pop up like a cork toward the top of the fluid? And the answer to that question is, it depends on the relative strengths of the buoyant force and the gravitational force. And if you want to express this in semi-mathematical language, we would just say it this way in English. If the gravitational force is greater than the buoyant force, then the ball is going to sink. However, if the gravitational force is less than the buoyant force, the ball is going to rise. That really is all that you need to remember here when it comes to isostasy. That's kind of the simple rule here. That's the take-home message on this slide. Okay, let's put this into practice now and see how this actually helps us understand vertical motion of the lithosphere in the real world. So again, remember, isostasy is just a balance of forces between the buoyant force and gravity. And so here we go. So let's imagine over on the left-hand diagram, we have a lithospheric plate shown in blue. And because the lithosphere possesses a certain amount of mass, remember mass is just stuff. Mass is, of course, made of atoms, and all objects in the universe possess mass because they're made of stuff, just like the lithosphere. So the atoms and the rocks and the minerals that make up the lithosphere all possess a certain mass. The more mass, the more gravity. And the gravitational force is wanting to pull the lithosphere downward into Earth's interior. That's what's shown right here. But hey, as we've talked about in the last couple of slides, there's also a net that is overall upward directed force called the buoyant force that's wanting to push the lithosphere upward. And the bottom line, you can kind of see it here in orange, is that if the gravitational force is less than the buoyant force, we get isostatic rise and the land pops up. On the other hand, if we get a situation where the gravitational force acting on the lithosphere is greater than the buoyant force acting on the bottom of the lithosphere, we get isostatic subsidence. The land will settle. And in the case of that right-hand diagram, one of the main contexts in which isostatic subsidence occurs is when Mother Nature deposits a lot of sediment in one place really rapidly. In effect, we're weighing down the cargo ship with a lot of cargo. And what's the cargo in this case, using this analogy? Well, the cargo is all of this sediment that's filling up that depositional basin. That sediment weighs a lot. It possesses a lot of mass. And so if Mother Nature piles up a lot of sediment in one place really rapidly, maybe on the order of hundreds or thousands of meters of sediment within, just a few thousand or a few million years. In effect, Mother Nature is adding more weight and more mass to the top of the lithosphere. In the same way that if we add more ice to the top of an iceberg, the iceberg will sink a little bit in the water. This is what's happening to the lithosphere in areas of rapid deposition. The lithosphere sinks isostatically, the land settles. Okay, let's do a quick concept check. So within the last few thousand years, great thicknesses of sediment have been deposited on the Mississippi River Delta, the area that I've circled there, where the river flows into the Gulf of Mexico, just southeast of New Orleans. So based on this condition, would the circled area be experiencing isostatic rise, isostatic subsidence, or would it be an isostatic equilibrium with neither rise nor subsidence occurring? So I'll give you perhaps 10 or 15 seconds to see if you can think that through and see if you can pick the correct answer to the question there. Okay, what did you get? Well, hopefully you picked number 2. In this case, we get isostatic subsidence. And there, on the bottom of the slide, I've shown the situation in cross-section as opposed to map view. And you can see there that the Mississippi River is depositing a lot of really heavy sediment on top of the sea floor, creating the Mississippi River Delta. That's what a delta is. It's just a plug of sediment, if you will, building up on top of the seafloor or on top of a lake bottom where a river flows into a stagnant body of water. Okay, so in the case of the Mississippi River around New Orleans, that sediment-laden river has deposited a lot of sediment on top of the seafloor in the area that I've circled. And just like that cargo ship analogy, in effect, we're weighing down the lithosphere from above, and that means that the gravitational force is going to temporarily exceed the buoyant force underneath the lithosphere, and the area that I've circled is going to settle. The land is going to subside. We're going to get isostatic subsidence in this case. And in fact, if you were to visit New Orleans, it's a little bit disconcerting because from the city and even from the French Quarter, you actually have to walk uphill to get to the river. So if you're here, you actually have to walk uphill to the top of the levee to get to the river level at flood stage. That is to say that most of the city of New Orleans is below the top of the Mississippi River, particularly when the river is at flood stage. And not only that, but the entire city, almost the entire city, is below sea level. And there are a lot of reasons for this, but relevant to this discussion, one of a number of reasons why much of New Orleans is below sea level is simply that this whole area is undergoing isostatic subsidence as a result of these delta sediments that have been deposited in the New Orleans area in just the last few thousand years. So again, all of that mass, all of that sand and silt and clay flushing into the New Orleans area from the Mississippi River is weighing down the land. It's weighing down the entire lithosphere. And in this case, the gravitational force exceeds the buoyant force, and so the land is settling isostatically. And that makes flood hazard a real concern in the New Orleans area, as we'll talk about a little bit later in the course. Okay, let's try another concept check question. So here we have a cross-section of an orogen, a mobile mountain belt. And the question is, can erosion contribute to mountain building? So we have an eroding mountain belt, and can that process of erosion actually contribute to the maintenance of the mountain itself? So I'll give you 10 seconds or so to look at the various possibilities and see if you can pick the correct one. Okay, what'd you come up with? Well, somewhat strangely, and maybe counterintuitively, it turns out that yes, erosion can actually contribute to mountain building, specifically because erosion can trigger isostatic rise. So let's think this through here. So notice that Mother Nature is wearing away the top of the mountain here by erosion. So all of this mass at the top of the mountain is being removed. It's probably being carried elsewhere by rivers and glaciers, that sort of thing. Remember that the gravitational force depends on the mass of the mountain itself, the mass of the lithosphere. And because Mother Nature is eroding away the top of the mountain, she's removing that mass so that the mass of the lithosphere is going down. That means that the gravitational force is becoming less and less as erosion is happening, wearing away the top of the mountain. But the buoyant force pushing upward on the lithosphere at the base of the lithosphere isn't changing, at least not at first. And so we get a situation where, particularly if we have rapid erosion, we get a situation where temporarily at least, the gravitational force becomes less than the buoyant force. And another way to say that, of course, as I've said it here, is that as a result of that erosion, the buoyant force temporarily overpowers the gravitational force, and because of that, buoyancy wins and the mountain rises isostatically. It seems kind of strange, doesn't it? But actually, yes, mountains last longer on planet Earth as a result of erosion and isostatic rise. And by the way, although the lithosphere will rise even as it's eroded, it almost never gets back up to its original height. In general, as a result of erosion, the mountain will rise up to about 80% of its original height. But the take-home message here is that, yes, in fact, erosion actually maintains mountains because it triggers isostatic rise. So yes, in some sense, erosion helps build mountains. That's the message here. Well, here's an actual example from my travels of where this is happening. As I probably talked about, I spend a lot of time every summer on the island of Iceland. I lead trips there for people. And this is a place that we visit in southern Iceland. It's one of the best known waterfalls in southern Iceland, known as the Skógafoss waterfall. And what's interesting about the Skógafoss waterfall is that that cliff over which the waterfall is plunging is an ancient sea cliff that formed at sea level a mere 13,000 years ago or so. And so quite literally in that right-hand photograph, ocean waves were lapping at the bottom of that cliff as recently as 13,000 years ago. Well, what's going on there? Nowadays, if you go visit the Skógafoss waterfall, the base of the cliff is over 200 feet above sea level. So what's going on here? Well, the take-home message is simply that since the end of the last glacial maximum, Iceland itself, the entire island pretty much has been popping upward isostatically like a cork. Iceland as an entire island has risen by, in some places, over 100 meters. That's over 300 feet vertically in just the last 13,000 years due to isostatic rise. And what's going on here? Well, you can see in those left-hand diagrams that I've drawn that if we go back to the Skógafoss waterfall 13,000 years ago, Iceland itself was sort of weighed down. It was pushed downward by the weight of the massive ice sheet that covered pretty much the entire island. And it's at that point that the Skogafoss waterfall formed right at about sea level around 13,000 years ago. And around that time, around 13,000 years ago, the climate in Iceland, in fact, the climate worldwide was changing and warming really dramatically and really rapidly. And so within no more than maybe a century or a century and a half, almost all of the ice that was covering the entire island of Iceland completely melted away. And that's akin to unloading the cargo ship that I talked about earlier. And as a result, the entire island of Iceland has been rising isostatically ever since 13,000 years ago. It's been popping upward like a cork. And so in this simple model that I'm presenting, it's not so much that sea level is changing. What's happening is the island is rising isostatically due to the removal of the ice from the top of the island around 13,000 years ago. And by the way, there are many places in Iceland, including the area of the Skogafoss waterfall, that are still undergoing rapid rates of isostatic rise on the order of, in some places, up to about 10 millimeters a year. In effect, the island of Iceland is still popping up isostatically as a result of climate change around 13,000 years ago. Okay, I think we'll go ahead and end this, this first narrated PowerPoint, and then we'll pick things up again for the second half of this PowerPoint.